So we're going to go back a bit and in this unit 2.3 touch back on material covered in chapter 5 dealing with stress and strain or elasticity. So this was more appropriate, I think, for the current chapter that we're in, chapter 9, but we need to go back and introduce some of these topics. The first is deformation. When an object is deformed in physics, it changes its shape due to the application of a force. So imagine a diving board, walking out on a diving board and having the diving board bend. That's a deformation due to the force or the weight of the person at the end of the diving board. If there is no weight at the end of the diving board hopefully returns back to its horizontal position. Now, small deformations can follow a principle called Hooke's law. Hooke's law is a relationship between the force applied to an object, the length of the deformation of that object, and these two things are related by a constant called k, lowercase k, which is a spring constant. So k is basically the slope of the line between the deformation and the amount of force. So a large k, a large spring constant, means that for a given force, there's a small deformation. If you want a large deformation, you need a very large force for a large spring constant. A small spring constant means that for a given force, there's a large deformation. So you can think of the spring constant as to the stiffness of the material. How difficult is it to imagine the old springs on the old automobiles for suspension? Those are very stiff springs. They're designed to hold the force, the weight of a car, or at least 1/4 of the weight of a car, one for each tire. So those have a very high spring constant, whereas a slinky, on the other hand, a metal slinky, would have a very small spring constant. A small force ends up giving you a very large deformation. So Hooke's law, the idea behind it, again going back to my diving board analogy, a given force will cause a deformation, but that deformation leaves when the force is removed, ideally. So in the case of a slinky, when you put the slinky back together, the slinky looks like it did when it was new out of the package. However, if you apply a large enough force on an object, you can actually go past its elastic region, if you will. You move to an area where Hooke's law is no longer obeyed, and this simple formula no longer applies. And the example of a slinky, some of you might have experienced this. If you take a metal slinky and you stretch it, and you stretch it, and you stretch it, and you stretch it as hard as you can, when you let it go, it does not return back to its original shape. It is permanently deformed. So you end up with this permanent deformation. When you have too great a force, you create a very quickly extend the length of the object. For the diving board analogy, imagine rather than having 1 or 2 or 3 or 4 people, the diving board just has more and more and more people. Eventually that diving board could break because it's past its elastic region. So Hooke's law is only obeyed for, depending on the material, for small range of forces from 0 to some small range of forces gives you a linear trend. So this line here is straight, and the slope of the line is given by k, or actually 1/k, technically, because this is y and this is the x-axis. So the relationship between force and the deformation is given by the spring constant k. So we have this relationship here. Most materials have some kind of elastic potential, right? Wood does, metal certainly does. But if you exceed the internal forces and things start breaking inside, the bonds start breaking, you can actually get permanent deformation out. You can snap the piece of wood, bend the metal, measure a crowbar, right? A crowbar is designed to be used to put some torque, and we'll talk about that later, place some force to lift up an object. But take that crowbar, if you could apply too much force to it, you could bend it, permanently deforming it, not having it come back to its original shape. Now that's usually beyond the scope of human ability, but you can't imagine a situation, the old superhero movies where they bend the iron rod, giving you a permanent deformation.